Hi everyone, this is Esty Kelman of Tel Aviv University. I'm here to present the paper towards a proof of the Fourier Entropy influence conjecture. This is joint work with Guy Kindler, Noam Lifshitz, Minzer, and my advisor, Muli Safra. In this talk, we'll state the Fourier Entropy influence conjecture. We'll see why it's so important, and some of our results getting quite close to it. Let's start with basic notions of analysis of Boolean functions. So what is a Boolean function? This is a function of n input bits and output of 1 bit. You may consider these bits as 0, 1 values or -1, 1 values. There is no crucial difference between those approaches. It's a bit more convenient for us to use the -1, 1 notions. So that's what we are going to use. A nice fact about functions over the binary hypercube is that every function has a unique representation as a multilinear polynomial. This representation called the Fourier representation of the function f, where x is the vector of input variables x1 to xn. The coefficients of the polynomial are real values and called Fourier coefficients. For every subset S of 1 to n, the coefficient of the monomial of the variables indexed by elements in S is denoted by f at S. Those monomials are so important that then they have a name. So let's define a character is a subset of 1 to n, which is associated with the monomial of all variables indexed by elements in S. So now, equipped with the Fourier representation of the function, there is a basic identity called Parseval identity related to Boolean functions. Say that for every function, the L2 norm of the values of is equal to the L2 norm of the Fourier coefficients up to some normalization. For Boolean valued functions with -1, 1, the L2 norm is always 1. And therefore, we get a bunch of non-negative numbers, the Fourier coefficient squared, that sum up to 1. We have a name for those type of numbers. It's called a distribution. They actually induced a distribution over the characters. So formally, the set of f hat squared is the Fourier distribution denoted by f hat. What can you do with this distribution? For example, we can calculate the average degree, which is the average of the monomial size. You can ask other questions about this distribution. What is the size of its support? How large are its entropies? A basic question is how this distribution differs between Boolean valued functions and general functions. So now we can state the Fourier entropy influence conjecture. We'll call it from now on the FEI. It says that for every Boolean function, the Shannon entropy of the Fourier distribution is at most the average degree. If you're not familiar with the Shannon entropy, it's okay. We will discuss it and define it formally later. And now I can tell you that our main result is a slightly weaker version of this conjecture. So after this opening, and we roughly know what is a FEI conjecture now, what are we going to see in the rest of this talk? So we'll talk about entropy, concentration, and how it's implied learnability. We'll see what is the total influence and why it's so important. We'll state formally the FEI. We'll see related results. And finally, we'll talk about a bit about techniques. We also see open questions. So let's start with concentration. So an important class of Boolean functions is the Fourier sparse functions. A function f is called the Fourier sparse if the Fourier distribution of f is supported on a small set of characters, which means that the number of characters for which the Fourier coefficient is not zero is small. Another related class is the class of concentrated functions. A function f is called concentrated if it is close to a Fourier sparse function. This means that most of its weight is concentrated on small set of characters. One reason those functions are interesting is that there are learning results about them. Kushilevitz and Minzer showed that concentrated and sparse functions are Pak learnable. More recent results by Gopalan, Kalai, and Clevans showed that they are also learnable in the agnostic settings. So let's see how it's related to entropies. So if a function has low Shannon entropy, this actually implies that it's concentrated. This just by using simple Markov inequality. And you get that most of the rate is concentrated on exponentially in the Shannon entropy many characters. So what we know about concentrated functions, they are learnable. And therefore we have the functions with low Shannon entropy also learnable. You might wonder maybe the other direction is also true. So if you think about it, even small weight might spread on too many characters and contribute arbitrarily to the Shannon entropy, make it large. So the answer is a big no. But still, concentration tells us something about entropies. So it's turned out that concentration implies low mean entropy. If you think about it, if most of the rate is concentrated on small set of characters, then at least one character of this set is a heavy. And this is exactly the meaning of mean entropy being small. Our results involve with Shannon entropy, concentration, and mean entropy. So let's talk a bit about the total influence. Lemma, the total influence, is the average degree. So what is average degree? We already know. But what is the total influence? Let's start with definitions, a basic definition of bit influence. So the influence of the bit I, of the variable I, is defined to be the probability over all possible inputs uniformly chosen. The probability that flipping the ith variable, flipping the ith bit, changes the output. In terms of the binary hypercube, you look at all edges in direction I. This is a fraction of sensitive edges. A nice fact about it is that the influence of the variable I equal to the summation of all Fourier coefficients squared for characters that include the variable I. If you think about it, this is quite reasonable because the only characters that are affected by the variable I, by flipping it, are characters that contain the I. And this is exactly the mass of those characters, according to the Fourier distribution. Now we can define the total influence, which is just the summation over all bit influences over all the variables. And now we get the corollary, the total influence equal to the expected degree. To see that, you just have to sum up all the influences according to the fact. And you see that each character counted for each of its variables, which is exactly its cardinality. So why this total influence is so important? A key question in the area of Boolean functions Suppose you have a Boolean function and you know that the total influence is small, say smaller than some k. So what can be said about the structure of this function? This question doesn't appear just out of the air. It comes up again and again in many areas in theoretical computer science, such as piece constructions, learning theory, extremal combinatorics, and many more. So the basic results about it are the KKL theorem and Entropies theorem, which says that a Boolean function essentially depends on 2 to the k variables. So if you think about k as constant, this is a very strong result. It says that a Boolean function with constant total influence depends on constant number of variables. You can think about larger k, it's still a very strong result. But if you think of k larger than log n, then it becomes meaningless. Just say that the Boolean function depends on 2 to the k, which is larger than n, but you have only n variables. So just meaningless. This phenomena appears in many results in Boolean functions. And so it's called the logarithmic barrier, because functions with total influence, which is significantly smaller than log n, we know to say a lot of things about them. But if the total influence is larger than log n, we essentially know to say nothing. The FEI trying to pass this barrier. So let's state the Fourier entropy influence conjecture. The FEI proposed by Friedgut and Kalai in 1996 intends to find a strong structure of functions with small total influence. It asks if for every Boolean valued function, the Shannon entropy of the Fourier distribution is at most the total influence up to some constant, where the Shannon entropy is the summation over all characters, the Fourier coefficient squared log 1 over the Fourier coefficient squared. This conjecture is still wide open. As we have seen, this would lead to a strong sparseness result. If the conjecture is true, a corollary of it is that the Fourier spectrum of f is concentrated on exponentially in the total influence many characters. While trying to make some progress with the FEI, researchers proposed weaker versions of it. One of them, which is very interesting, suggested by O'Donnell and others, called the Fourier mean entropy influence conjecture. They asked if the entropy influence inequality holds when the Shannon entropy is replaced by mean entropy, where the mean entropy is the minimum of log 1 over the magnitude of the Fourier coefficient among all characters. In fact, the mean entropy could be much smaller than the Shannon entropy, even for Boolean functions. So this relaxation could be strictly weaker than the original conjecture, even though it would imply the KKL theorem and many applications of the FEI can be concluded from it. This weaker version is as wide open as the original conjecture itself. What is so important about this conjecture that even though this question has long remained open, we are still investing time and effort in trying to solve it. So if it's true, it implies a strong structure of Boolean functions. For example, this could resolve Minzer's long-standing conjecture about the sparsity of DNF. Combining with Gopalan's learning theorem for sparse functions, this would lead to an agnostic learning algorithm for DNF. It would give a non-trivial result, breaking the logarithmic barrier. The original motivation was studying sharp thresholds, and this would improve those results. So let's see some related results. There were many attempts trying to attack this conjecture. It proved to be true for some specific classes and random functions for some families. O'Donnell and Tan showed composition theorems for the conjecture. Other works show different weaker bounds on the Fourier entropy using complexity measures. There were many attempts trying to attack this conjecture. It proved to be true for some specific classes and random functions from some families. O'Donnell and Tan showed composition theorem for the conjecture. Other works showed different weaker bounds on the Fourier entropy using other complexity measures. All the results about the FEI conjecture itself are certainly true also for the weaker version about the mean entropy. Also, some other classes and measures proved only for the mean entropy. In terms of total influence, the best previously known result is an upper bound with total influence squared. This follows from Friedbuch-Runter theorem. Since even for the Shannon entropy, bound of total influence times log n is quite trivial, this does not actually break the logarithmic barrier. And therefore, it sort of misses the point of the conjecture. One of our results is a better bound on the mean entropy passing this barrier. We say that for every Boolean function, the mean entropy of the Fourier distribution is at most the total influence times log of the total influence. This gets quite close to the conjecture because you have only this log term to get rid of. Even though this is not exactly the conjecture, we still get nice corollaries from it. And in fact, our results are even stronger than that. We prove a similar bound on the Shannon entropy of the Fourier distribution itself. So let's see it. Let us rephrase the Fourier entropy influence conjecture in terms of the Fourier coefficients. The purpose of it is to see the similarity between the conjecture and our main result. We can prove that for all Boolean functions, the Fourier Shannon entropy is at most the expected character size, except that you pay log of the character size in the expectation. For most reasonable functions, this is the same as total influence times log total influence. But for some odd functions, it may not be the case. Again here, the log term is what separates us from the conjecture. But we still get some useful insight out of this theorem. And indeed, our result is even more general. What happened if you look at the Shannon entropy, but up to a certain level? How does this relate to the total influence? Surprisingly, you can truncate both expressions at some level. And these inequalities still hold. We still pay this log s term, and we now have the additional total influence, which is okay because it's also appeared already in the conjecture. This result is much more flexible. You can choose any D you want, any level. And in the paper, we have some more variants. And there are variants that do not appear in the paper, but this is the main one. I would like to share with you some of our corollaries from it. So let's see. What if you choose to truncate the functions on level D equals to the total influence? Then what we get, a nice corollary, we call it the low degree Fourier entropy theorem, which say that for every Boolean function, the low degree Shannon entropy, which defined as the summation up to some degree, is at most the total influence times log the total influence. So this at least say that every Boolean function is close to a function with small Shannon entropy. And this leads us to a strong concentration result. So the other corollary is that the Fourier spectrum of the function f is concentrated on exponential in the total influence, log total influence, many characters. So we still have here the log term, but this result is much stronger than every previous known result. And this would lead to agnostic learning for functions with small total influence. Another result I want to share with you is about sharp thresholds. This is a bit stronger than our results related to the mean entropy. So what we say is that for every Boolean function, there is a small character such that the weight of it is at least exponentially small in the character size times log total influence. And you can see that as the character are getting smaller, the bound is stronger. And with this result, we strengthen the Bourgain-Calais result for graph properties. So after you have our results, and let's talk a bit about our techniques. So our main technical results is a series of correlation inequalities for low degree functions generalizes each other. Our techniques build on and improve techniques from the Bourgain-Calais work. The way we reduce degrees is random partition, which is a refinement of random restriction. So this is just a bit about our techniques. And let's end this talk with some open questions. So trivially, you can think of improving our results, maybe even prove the FEI itself. You can think about the lower degree FEI. Improving this would lead even to Minzer conjecture. Maybe we can find other applications for our techniques, for our correlation inequalities. Or if you get inside our techniques, maybe you even might think about applying it on AC0 related questions. Thank you for your attention.